When I announced my summer break, some viewers were disappointed. This is why I thought I will republish a few of my favorite videos from the past. I hope you will enjoy them. This video is about one of the essential concepts of electronics. I hope I was able to explain it more accessible than many other sources. The video is already 5 years old.
Grüezi YouTubers. Here is the guy with the Swiss accent again.
To keep a constant speed with your car on a mountain road, you have to adjust your throttle according the steepness of the road. This is not very comfortable, slow in reaction and also not very accurate. This is why engineers developed the speed control. Today I need a speed control for the fan of my wind tunnel, and I will show you how such a device can be built using an Arduino. Other than many descriptions and YouTube videos, I try to keep it simple but still useful and use also examples. After this video, you should be able to control motors of any kind for a stable speed. Now let's start. I have a wind tunnel consisting of a strong fan, a pipe and a reduction to increase airspeed. In a former video I described how to control the fan. For now we just have to know that I am able to set the fan speed using a pulse width modulated signal, also called PWM signal. I am also capable to measure the speed of the fan. So we have a simple system. This runs stable if I keep the PWM signal at, let's say, 500. As soon as I block the exhaust, the fan reduces its speed because it needs more power and the PWM signal does not rise. So the system is disturbed and the fan reacts with a speed change, exactly as if you would drive up a hill and keep your throttle fixed. What we need now is a so-called closed loop system consisting of the fan and the controller. The controller measures the speed of the fan and adjusts the PWM signal accordingly. I could do this manually, but I do not want to show you this example because it is quite clear that I do not have 4 hands to block the exhaust and adjust the PWM signal at the same time. In addition, I would be way too slow. This is why I use an Arduino Micro for that purpose. It can measure the speed and adjust the PWM signal. This can be done quite fast because Arduinos work in micro or milliseconds. Let's look now closer to the controller. It has 2 inputs, the actual speed and the constant speed I wish the fan should run. I call it set speed. With these 2 values, we can create a formula to calculate the PWM value. Because we want to minimize the difference between the set speed and the actual speed, we first calculate this difference. Based on this result, we can do different next steps. The simplest possibility is to switch the fan on if it is too slow and switch it off if it is too fast. Let's try it. It works astonishingly good. You hear the on and off switching, and if we look at the result, the speed builds up very fast and is very stable after that. Keep in mind that I record the values in Excel and only record every 100th value to keep the speed of the loop fast. This result is good because the reaction time of the controlling loop is very fast compared to the reaction time of the fan. If I build a delay of 500 milliseconds into the loop to slow it down, the behavior changes rapidly. We learn that the on-off controller is simple and okay if the control loop is much faster than the reaction time of the system. And if the switch is mechanical, we have to take wear and tear into account. If you Google, you quite often find the expression PID controller. What is this? How does it work? PID stands for proportional, integral, and derivative. These controllers consist of 1, 2, or 3 parts. The PWM signal consists of the sum of the 3 parts. The P part just multiplies the difference with a factor. The I part sums up all differences and multiplies this sum with a factor. And the D part calculates the spread between the last and the current difference and multiplies this spread with a factor. It is obvious that the 3 parts behave completely different. For this video, I will concentrate on the first 2 parts because this is sufficient for most of the motor applications in the Arduino field. You can extend your knowledge afterwards to the 3rd part if you need. I start with a P controller. This means that the I and the D parts are set to 0. Let's try now how the system reacts on a set speed of 2000 RPM. I set the P factor to 0.5. The speed is in orange color and the difference is gray. The left axis is for speed and the right for difference. The fan starts quickly, overshoots the 2000 RPM a little and settles quite fast on below 2000 RPMs. So we do not reach our goal to get constant 2000 RPM. At least we get a constant speed. Therefore, let's try with a big factor. P equals 1. Now the difference is smaller, but unfortunately the system oscillates. If we increase the factor to 5, these oscillations get bigger. We see that a P controller always keeps a different to the set speed and starts to oscillate if the factor is too big. This is why many controllers are enhanced with an I part. The formula is enhanced by summing up all differences into the variable integral. Because the PWM signal is the sum of both parts, P and I, we call this formula PI controller. The integral part gets bigger and bigger if a constant difference exists and should close the gap of the P controller. To start our test with the PI controller, we use the same factor as before and add a small I factor. The system overshoots more, but the difference at the end is much smaller. To avoid overshooting, I changed the factors to P equals 0.1 and I equals 0.001. Now the system behaves okay. It spins up fast and settles very close to 2000 RPM. Again, if I increase the I factor, the system starts to oscillate badly. Obviously, the I factor has to be much smaller than the P factor. Just for fun, I tried an I controller with I equals 0.001. This system starts slower than the PI system, but also settles to exactly 2000 RPM. Increasing the I factor also leads to oscillations. Interesting for me was also to observe how much the different parts contribute to the total in a PI controller. At the beginning, the P part carries the big load and the I part does not contribute. This changes quickly, and after a few cycles, the I part contributes nearly 100%. But after all the work, let's check the results of the wind tunnel. If I block now the exhaust, the RPM stays stable because the PI controller automatically adjusts the PWM signal. Job done. I hope it became clear on how these controllers work, and also that finding the right combination of P and I factors is a try and error process. Usually I use potentiometers or rotary encoders to adjust these factors and see the result real time, as I did with my robot. By the way, in this robot you find two independent PI controllers. One to keep the angle upright and the other to stabilize speed. But more about that in a later video. I hope this video was useful or at least interesting for you. Bye!